Hello everyone, welcome to the lecture. Today we are going to explore something that turned the physics world on its head. Albert Einstein's special theory of relativity. A step toward understanding the universe. And I promise at the end of this session you will be seeing space, time and light in a whole new way. Okay, quick question. Have you ever wondered if time moves the same for everyone and everywhere, or how light travel at same speed no matter how fast you are moving? Crazy, right? That's what exactly Einstein was trying to figure out, and trust me, he found some answers that blow your minds up. So let's dive in and make sense of it. So what we are going to do today, first we will be understand the historical background that led Einstein to his big idea. Then we will be learn his two core postulates, the foundation of special theory of relativity. We will explore some cool consequences like time dilation, length contraction, and why simultaneity is relative. And of course, we will see how all of this impact our real world technology and even space travel. All right, let's rewind a bit to the 17th century. You know Isaac Newton, right? He's the guy who said space and time are absolute. What does that mean? Well, it means that space and time exist independently, no matter where you are or how fast you are moving. In Newton's world, time is like an universal clock. If 5 seconds pass for you, then exactly 5 seconds pass for me and everyone else, no matter where we are in the universe. This view works well for most mechanical problems like falling objects or planetary motion. What does it mean that space and time are absolute? So here's the kicker. Absolute absolute time. According to Newton, absolute space is like background canvas where all event occurs. No matter how fast you are moving or whether you are standing still, space around you remains the same. Imagine you are walking across the room where you will be walking fast or slow. The space between you and the wall is the same, right? So that's absolute space in action. What about absolute time? Well, time is ticking for everyone at same rate. If I'm standing on Earth and you are zooming in spaceship, our clock tick at exactly the same speed, no matter what. If, if 5 seconds pass for you, the same 5 seconds pass for everyone else in universe. Then came James Clerk Maxwell in 1860s, and he made a big breakthrough. Maxwell equation unified electricity and magnetism into electromagnetism. Now, he was the guy who first said light is an electromagnetic wave traveling at fixed speed of 300,000 km per hour and kilometer per second. That's about 186,000 miles per second. But wait, this is the guy Maxwell. special equation raises a huge question. Speed relative to what? If light is a wave, shouldn't it need something like air for sound to travel through? Here is this picture shows how light travels. As I said earlier, light is electromagnetic waves. So this is electric field and this is magnetic field. So light travel perpendicular to both electric and magnetic field. So to describe this medium, we came up with scientists came up with new concept, the idea of mysterious luminiferous ether, which also called as ether hypothesis, a medium that supposedly filled space allowing light to travel through it. Here's the thing. Physicists thought this ether was everywhere. It was the invisible substance that filled space. They thought it was the absolute reference frame, the thing against which we could measure movement and test it. They came up with a genius experiment. They thought, okay, if Earth is moving through the ether, we should see changes in speed of light depending on which direction we are moving. So one experiment is conducted to explain this, which we known as Michelson-Morley experiment. Let me paint a picture for you. In 1887, Michelson and Morley set up a groundbreaking experiment. They built a interferometer. This is a device that split light into two beams, send them in different directions, and then combine them back to check for any phase differences. Now, here's the important part. If Earth is moving through the ether, the two beams should travel at different speed, depending on whether they are moving with or against the ether. But guess what happened? No phase difference was observed. The light beam come back exactly the same no matter which direction they were traveling. This was huge shock to scientists because it meant one of two things. Either the earth isn't moving through the ether, which was hard to believe that time, or ether doesn't exist at all. And maybe light is just behave differently than we thought. So here's the guy who revolutionized this. Einstein revolution 1905. Enter Albert Einstein. This is the guy, mysterious one guy. Age 26 in 1905, he didn't just tweak on Newton's law. No, he completely redefined our understanding of reality. He rejected the ether and introduced his bold new theory of special relativity. The two core ideas of special relativity are the law of physics are same for all observer in uniform motion. The speed of light in vacuum is constant for everyone, no matter how fast they are moving. So laws of these two people, one is sitting and one is running, is same for all inertial frames. Okay, so now we have two postulates of special relativity. The first one tells us that law of physics work the same in all reference frames that are moving at constant speed. The second one tells us the light travel at the same speed for everyone, regardless of how fast you are moving. So, as the consequences of these two postulates, we observe these effects. First one is time dilation. So, we get something really cool, time dilation, which says, imagine you are traveling at near speed of light. For you, everything seems normal. Your clock ticks just like always. But to someone who's standing still, your clocks look like it's slowing down. So, times move slower when you move faster. Moving clocks ticks more slower. And the slowing factor is here. This is the factor who slows the time. The consequences or example of this effect is twin paradox, which says if one twin on the earth and other goes on a spaceship, then according to time dilation effect, the traveling twin will be a slower when they reunite. Now the traveling twin will be younger than the earth's twin, which was really cool. So next, major consequences of these postulates are length contraction, which is fascinating result of special theory of relativity. Now we don't worry, we are not going to make train vanish or anything, but get this. According to Einstein theory, when an object moves really fast, close to speed of light, it actually shrinks in the direction of motion. Not to the person inside the object, but to someone who's watching it from stationary point. Let me give you a classic example. Imagine a train moving at very high speed, close to the speed of light. Now, the person on the platform standing still and train looks shorter than it would be if it were at rest. But to the person riding inside the train, nothing seems to be observed because how motion affects space in special relativity. The, so, faster the object moves, the more it contracts, and only along the direction of its moving. Cool, right? It's like space itself starts stretching and squeezing depending on how fast you are going. That's length contraction in action. And this is the factor in which the length contracted. The last one last crazy idea of relativity of simultaneity. Let's say lightning striking at both ends of the moving train. To an observer standing still on the platform, the striking happens at different times because the train is moving. But to someone on the train, the striking are simultaneous. That's the magic of relativity. So it says events simultaneous in one frame may not be in another. Lightning strike at both ends of the train, which is the example I already given you. So how does this all apply in real world? Well, GPS satellites need to account for the time dilation to stay accurate, and particle accelerator like CERN particle experience time dilation as they zoom close to speed of light. Even cosmic ray reach to earth thanks to this effect, and time dilation in space travel, which we already observe in twin paradox phenomena. So let's quickly summarize. Space and time are not absolute. The speed of light is constant for everyone. The motion changes time, space, and mass, and Einstein completely changed how we see reality. Now it's end here. Thank you so much for sticking with me through this mind bending journey. I will leave you with one of my favorite Einstein quotes: imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world. Keep thinking, keep imagining, and keep exploring.